Good afternoon, everyone. My name is Avi Suntorian. I'm from Mechanical Survey, Tavasar. So today's AAT for engine design topic is electric fan blade vibration reduction. Without moving further reasons, let's just get into it. Introduction. Fan blades convert rotational energy from the motor into airflow due to imbalance, aerodynamic loading, or mechanical defects or vibrations develop. These vibrations cause noise, fatigue failure, reduce efficiency. Now the goal is to understand vibration sources and implement reduction methods. So the introduction, you can go through it. So yeah, it's simple. The goal is to understand vibration sources and implement reduction method. That's it. Simple. We'll go to the next slide. Objective. Objective is to analyze causes of fan blade vibration here, which means we need to first analyze causes of fan blade ka vibration and then study the dynamic behavior of rotating fan blades. The next thing we do is study the dynamic behavior of rotating fan blades. And after this, we need to explore methods for vibration reduction and then the structural material and controls based. So you understand, we need to explore the methods of vibration reduction, structural material, and control based. After all this, we need to evaluate experimental simulation approaches for vibration suppressions. Nothing but experimental and simulation approaches. So yeah, these are the objectives. Sources of vibration. Mass imbalance. Mass imbalance means uneven blade weight or density. Aerodynamic forces, which means unsteady airflow or weak effects. Right. Mechanical looseness. Mechanical looseness means bearing wear or misalignment and all. And then we have resonance. Resonance. Yeah, resonance means blade natural frequency matching excitation frequency. And then we have manufacturing defect, uneven shape or rough surfaceness, surface roughness. Yeah, and then we have motor electromagnetic pulsations. So these are the sources of vibrations. These are the main sources of vibrations. Yeah, and then we have types of vibrations and fan blades. There are totally four types: causes and effects. So first type is torsion, second type is bending, third type is axial, fourth is resonant, right? In torsion, the cause is shaft twist due to torque. The effect is noise and reduced power, right? Yeah. And then the second type is bending. Bending, the cause is blade deflection due to lift force. And then the effect is crack initiation. And then we have axial, causes motor shaft misalignment, effect is bearing wear. And then fourth one, final one is resonant, causes frequency matching, and effect is catastrophic failure. These are the types of vibrations in fan blades. And then we have mathematical modeling. Uh, Fan blade modeled as cantilever beam with rotating motion. Governing equation of transverse vibration is one, which is EI, E bar 4y, EX4, and then plus rho A d2y by d2 dt2, and then that's equals to 0. And then we have natural frequency, which is omega n equals to k by whole root of k by m, where E is modulus of elasticity, I is area of inertia, m is mass per unit length, k is stiffness matrix. Simple. This is the mathematic modeling of that, and we go to the next one. Experimental analysis. Model testing used to identify vibration modes. Accelerometers attached to blade record displacement and acceleration. FFT analysis determines dominant vibration frequency. Then test setup includes test setup includes speed, motor and shaft assembly. Other one is variable speed control. Other one is vibration sensors on each blade tip. So these are the three test setup that's main: motor and shaft assembly, various speed controls, vibration sensor on blade tip, and then FTF analysis, and then accelerometers are main. Uh, Model testing used to identify vibration modes. Simulation and FEM analysis. Conducted in ANSYS steps. First step is to do a 3D model of fan blade. Create it in aluminium or plastic 3D model. And then the second step is materials property assigned. You need to understand what the product is about, and we need to assign according to that the materials that we are going to use through material properties. And then the third step is boundary conditions. Fixed at hub, T at tip. And then the fourth one is model analysis performed. So these are the outputs are nothing but natural frequencies, mode shapes, stress and deformation contours. These are the outputs, natural frequencies, mode shape, stress and deformation contours thing. And the next slide is vibration techniques. There are five vibration techniques. Dynamic balancing ensures center of mass lies on rotational axis, done by adding or removing small weights. Okay, that's dynamic balancing. Second one is structural optimization. That is blade geometry modification, shift natural frequencies. And the third point is damping enhancement. Rubber or viscoelastic mounts to absorb vibrations. And then the fourth point is material selections. Use of composite materials with higher stiffness to weight ratio. Fifth one is active control. Sensor detect vibration, actuators apply counterforce. Simple as that, right? And the next one, design optimization. Example. The example here is blade material we need to be taken. ABS plastic. E equals to 2.3 GPa. Rho equals to 105 A. 1050 kg by M3. And then natural frequency target. Okay. That is 1.5 into operating speed frequency. Among all this, we using topology optimization was reduced by 15%, and vibration amplitude reduced by 35%. The plate material is ABS plastic, A equals to 2.3 GPa, rho equals 1050 kg by M3. Using topology optimization, mass reduced by 15%, and vibration amplitude reduced by 35%. Results and discussion. Model analysis revealed first natural frequency and 180 Hz safely. Operating frequency 60 Hz. Dynamic balancing reduced peak amplitude from 0.8 mm to 0.25 mm. Composite laser reduced total noise by 68 dB. Improved service life and motor efficiency. Conclusion. Ambient vibration originates mainly from imbalance and aerodynamic effects. Effective reduction involves balancing, design tuning, and damping. FEM-based design helps predict and avoid resonant future improvements, smart materials, piezoelectric damping, real-time vibration monitoring systems. Thank you.